Welcome back. Today we're going to keep talking about the fundamental building blocks of matter. In the last lecture, we talked about ways in which materials can arrange themselves just as atoms. So we saw that noble gases and metals consist just of those atoms arranged together. Two other fundamental building blocks of matter are molecules and ions, and we'll find that that is when atoms arrange themselves with other atoms. They combine with other atoms in order to find new substances. It's a very interesting topic in chemistry, so let's just dive right in. So a molecule forms when two or more atoms bond together with covalent bonds. And as we go through this, we'll learn that that's not the only way that atoms can combine. But a molecule is formed when two or more atoms bond together with covalent bonds. And we'll talk more about what exactly a covalent bond is in the next lecture. So here's a question for you. Is it true that all molecules contain at least two different kinds of elements? Why don't you pause the recording and think about that? Welcome back. Indeed, that is not true. Molecules can form with a combination of the same kind, with two or more of the same kind of elements. So here's another question. Here are three different substances. We've got a diamond, we've got some charcoal briquettes, and we've got some graphite. What do these items have in common? Are they all man-made? Are they all mined from the earth? Are they all made of only carbon atoms? Or none of the above? Well, it turns out that all of these items are made from carbon atoms. Notice how different these substances are. Diamond has a very different set of properties than do charcoal briquettes. And if you don't believe me, try giving your sweetie a charcoal briquette and see how excited they are. So this is one of the fundamental points, I think, that I want to make as we go through this chemistry unit. And that is that the properties of the elements that make up the compound are different than the properties of the compound itself. So all three of these items, graphite, charcoal briquettes, and diamonds, they're all made of just carbon atoms. But because those carbon atoms arrange themselves molecularly in different ways, then we end up with very different properties. We'll talk more about that as we go along. So molecules can be different types of atoms, but they can also be made from the same types of atoms. If you take a deep breath, then you just breathed in a whole bunch of molecules made with two of the same kinds of atoms. The air we breathe is about 78% nitrogen molecules and about 21% oxygen molecules. Both of those are what we call diatomic molecules because they are molecules formed of two of the same type of atom. And here we see this is just a way of representing these molecules. Each one of these bars represents a covalent bond. And again, we're going to go more into that in the next lecture. But for now, you just need to know that this is a pair of shared electrons. Each one of these bars represents two shared electrons. So we see here that in the hydrogen molecule, it consists of two hydrogen atoms bound together with one covalent bond. One covalent bond represents two shared electrons. Here we see oxygen. This is the diatomic molecule oxygen. It consists of two oxygen molecules. There are two covalent bonds. We would call that a double bond. Two covalent bonds representing a total of four shared electrons, two for each bond. Here we see nitrogen, N2. Again, another diatomic molecule. And it is held together with three covalent bonds. So we see three covalent bonds and a total of six shared electrons. Molecules can also form with different types of atoms. For example, water, our good friend water, H2O. That's two hydrogen atoms and one oxygen atom. it forms a molecule. And again, those are held together with covalent bonds. Here's carbon dioxide, a major constituent of the air we breathe out. And of course, alcohol right here. This is the kind of alcohol that you might drink in a beverage, if you're old enough. Here is another way to represent these same molecules. And these are all just pictures from a simulation that we are going to do this week. Here we see the covalent bonds represented as this little stick right here, as these little sticks right here. So again, we're going to come back to that. Methane, carbon dioxide, and of course here's our good buddy, water. A whole lot of the substances around us that we interact with on a daily basis consist of molecules. Here's water, H2O, sugar, C12, H22O11. So that's a big old molecule. And it's also a delicious one. Here's dry ice, also a molecule. So this is one carbon atom, two oxygen atoms, all held together with covalent bonds. Iodine is a diatomic molecule. It consists of two iodine atoms bound together with a covalent bond. Now, again, one of the central points here is that the properties of the molecule are different from the properties of the individual atoms that make up that compound. For example, water is one of our favorite compounds as humans. It consists of two hydrogen atoms and one oxygen atom. And let's look at both of these. Hydrogen, in its atomic state by itself, it's a gas. It's highly flammable. Maybe some of you have heard of the Hindenburg, the famous dirigible blimp-like thing that went up in flames at the beginning of World War II. It was full of hydrogen. It explodes. It's highly explosive. A fuel cell runs off of combining hydrogen and oxygen to make a car go down the road. At any rate, hydrogen just is super not water. It's just not even remotely like water. It shares none of the same properties as water. Same thing with oxygen. Oxygen, we breathe it, right? We run on oxygen. Our bodies run on oxygen. And the properties of oxygen are just totally different than the properties of water. If you don't believe me, try taking a deep breath of water. Don't actually do that. Okay. So that's one of the central points here, right? The same ingredients here, hydrogen, oxygen, carbon. And we can make sugar, we can make dry ice, we can make water, we can make methane, we can make alcohol, we can make all kinds of different atoms. We can make plastic, right, out of carbon, hydrogen, and oxygen. So all of these different substances are made of the same atoms. The properties of the atoms that make up the compound are different from the properties of the compound. That's one of the important points that I'd like to make as we go through this section. So, how do we describe a molecule? Well, we use a molecular formula, which I've actually already put some of those on the slides here, and you've probably seen this before. A molecular formula is the name of a molecule written using symbols and numbers. So, for example, we've already looked at this molecular formula. It's oxygen 2, O2. This means that there are two oxygen atoms in this molecule. We kind of went over some of these. Here is carbon dioxide. There is one carbon and two oxygens in this molecule. That's how this is written. So notice if you don't see any subscript at all, it's an implied one. Here's this guy right here. This molecule has 6 carbons, 12 hydrogens, and 6 oxygens. Now this one is written so that the hydrogens are all spread out, and so are the carbons. They're separated too. Why? Well, because there's actually something that's important about this group right here. That's something important about this group of atoms right here. In fact, this group right here forms something called an ion, which we're going to talk a little bit more about here in just a minute. But suffice to say that sometimes chemists write these out with the hydrogen separated, but we're not going to get into that. There are some rules. There's a lot of rules for exactly what order the the elements should come in and whether you should group them together or write them all out separately. We're not going to get into that at all. So if you see something like this, we could just count this up. This has 3, 4, 5, 6 hydrogens. It has 2 carbons and 1 oxygen. Okay. So those are molecules, and molecules are one way for atoms to combine to form compounds. Another way that atoms can combine to form compounds is as ions. Now, I've already mentioned that an ion is a charged atom, and that is true. Here we see examples. This is a sodium ion. This is a chlorine ion. This is a calcium ion. This means that this is a positively charged sodium atom. If it's positively charged, it must have lost 1 electron. This is a negatively charged chlorine ion. If it's negatively charged, it must have gained an extra electron. Here we see this is calcium 2+. So this is a calcium atom, and it has a 2+. So this must be a calcium atom that has lost 2 electrons. Of course, if we had a calcium atom, another way to make a calcium atom charged, you might think, would be to add a proton. Well, why don't we ever talk about adding and removing protons? Well, because the protons are tightly bound, recall, within the nucleus, and removing them causes a removing them causes a nuclear reaction. That's not what we're talking about. We're talking about chemical reactions, which involve the electrons. The other thing is, if I added 2 protons to calcium, I wouldn't have calcium anymore. I would have a different element, because the number of protons defines what element we have. So an ion can be just an atom that's lost or gained electrons, but it could also be a group of atoms. And so this is one particular group of atoms that's got 1 extra electron associated with it. And so it has a negative charge. Here is a group of atoms that have a positive charge, and here is a group of atoms that have a doubly negative charge, 2 negative. That means this one has 2 extra electrons. 2 extra electrons right here. So if it is a positive ion, we call that a cation. Meow. And that is a charge, an ion with a positive charge. A negative charge is called an anion. Not an anion, but an anion. That is an ion with a negative charge. So here is a question for you. If the red balls in the picture represent protons, what atom do we have? Or, what ion do we have in the picture? Why don't you pause the recording? You're going to want your periodic table and try and figure this out. Okay, so if we look at our periodic table, the red balls are protons. So we have 1, 2, 3, 4 protons. Which element has 4 protons? Well, we need to look at our periodic table, look at element number 4. We'll find that element number 4 is beryllium. Okay, so it's definitely beryllium. It's definitely A or B. Now, is there more electrons or are there more protons? Or are they equal? Well, I see 4 protons and 3 electrons. Therefore, this is an ion. We have more positives than negatives. We have 1 more positive than negative. Therefore, it is a cation of beryllium. Matter that consists of ions is also all around us. The most delicious version would be table salt. Table salt is made of a sodium ion and a chlorine ion. It turns out that the sodium ion is the positive half, and the chlorine ion is the negative half. Now, what we'll learn is that these are compounds that are held together not with covalent bonds, which is a sharing of electrons, but rather with ionic bonds. And in an ionic bond, the atoms don't share the electrons. One atom actually steals it from the other. One atom steals the electron from the other. So in table salt, we see that sodium loses an electron completely. Where does it go? Chlorine steals it. So sodium becomes positive and chlorine becomes negative. Well, we learned in the last section, what happens if you have a positive charge We learned in the last section what happens if you have a positive charge and a negative charge. Well, they're attracted to each other. It's an electrical attraction, and they'll stick together. And the result is delicious. Now, it's really important here to point out, again, the properties of the compound are different from the properties of the atoms that make up the compound. So back to table salt. Table salt is, again, a sodium ion and a chlorine ion. What are the properties of sodium? Well, sodium is highly reactive. You can't actually go online and buy a sample of pure sodium because it actually explodes. You can actually make a bomb out of it. If you put it in water, it combines very rapidly with the water, and it releases hydrogen gas, which is dangerous. So sodium, pretty dangerous all by itself. How about chlorine? People put minute amounts of chlorine in their swimming pools. Why? Because it kills everything it touches. In World War II, the Nazis used chlorine gas as a chemical weapon, and there's some evidence that the Syrians have been doing it more recently. It is a deadly poison. So you combine sodium, something that's explosive, with chlorine, something that is a deadly poison. And what do you get? Something delicious. The properties of the compound are different from the properties of the atoms or ions that make up the compound. The properties of the compound are different from the properties of the elements that make up the compound. Okay, other ions that are very useful to us humans: baking soda, Tums, Epsom salts. What do we notice about all of these things? And again, we'll talk more about this in the next lecture. But notice sodium. Why don't you look at your periodic table? Is sodium a metal or a nonmetal? Sodium is a metal. Chlorine is a metal or nonmetal. Check it out. So, sodium is a metal. Chlorine is a nonmetal. So we see here that table salt is a combination of a metal and a nonmetal, and it forms an ionic compound. Baking soda, sodium is a metal. These guys are all nonmetals. A metal combined with a nonmetal forms an ionic compound. Calcium is a metal. These guys are nonmetals. A nonmetal combined with a metal forms an ionic compound. Magnesium is a metal. These guys are nonmetals. Again, a metal combined with a nonmetal forms an ionic compound. Here is a zoomed in picture of table salt, sodium chloride. It forms this crystal lattice where the atoms arrange themselves in this square pattern. Kind of cool that the microscopic symmetry is reflected by the macroscopic symmetry. If you look at a tiny crystal of table salt, you will find that it is basically cubic in nature. It basically looks like a little box. And what's cool is that that macroscopic symmetry is reflected in the microscopic symmetry. That is how those ions arrange themselves in what we would call a crystalline lattice. A lot of minerals are ions. So these are all pictures of various minerals. If you've ever gotten to go into the mineral room at the Museum of Nature and Science in Denver, they've got a whole bunch of really cool ones. But a lot of these are all ions. If you've seen those little water spots that form, I don't know, after you wash your car with your hose, or maybe in the bottom of a glass where the water has evaporated, those are all ions that have been left behind, that have been absorbed or dissolved into the water, and then when the water evaporated, they got left behind.